Hi everyone, welcome back. Slightly delayed video today. It's been a busy weekend. It's been a busy week and I haven't made as much progress as I'd hoped, but we'll get to that in a minute. Let's get into it. So, like I say, not got as much done as I'd wanted, although preparing this video made me realise I've actually got more done than I realised. So we're going to talk about a little piece of refactoring that I've done, a new render mode that I've added, and fault type determination, and then we'll look at what we're doing next. So for anyone new, we are building a tectonic plate simulator to build worlds for a real-time strategy game. And where we left last time, we had shared plate boundaries working, plate points moving, and we were just starting to look at how to make the boundaries of the plates themselves move. So first thing was a piece of refactoring. So I've had a recurring rendering bug where the position and colour buffers are separate, and filling them independently they can get out of sync. If you write, say, 4 vertices and 5 colours, you will have a problem where the next set of vertices have the colour from the previous vertex. Now this doesn't actually crash, it just colours things wrong, which doesn't sound like a big deal, but when you're using colours to represent things in the model, it's very misleading. It makes you think you've got the maths wrong, it makes you think you have a bug somewhere in the code that is setting the properties that are being coloured, not in the rendering code. And this has caught me out 3 times now, and I've wasted quite a lot of time each time. So I've gone and created a help function that can update both buffers simultaneously for creating some common objects like points. And I haven't had this problem since, but it did take a bit of effort to come to that solution, and also to then go and refactor all of my existing rendering code to use it. Second job was creating a new rendering mode. So we need quite a bit more info relating to boundaries. I'll talk about that in a second when I show you the new rendering mode. And the plate point mode was already quite cluttered, so I've created a new boundary rendering mode which shows just the boundaries. So let's have a quick look at that. So this is a static image of the boundary rendering mode. So what information do we have here? We have the direction of movement and speed of the plate represented by an arrow here. Now you might remember when we would see plate points moving, because of the sampling artifacts, it could be quite difficult to tell which direction they were moving in. Similar to if you look at a car wheel on a video, sometimes it looks like it suddenly starts going backwards. Same problem, just an artifact of frequency sampling, nothing you can really do about it. So instead of actually watching them move, we just draw the direction. It's a lot simpler. We have the boundaries rendered and they are coloured by boundary type. We'll get to that in a minute. But as well as that, we have these straight lines. Now what these represent is the direction of the boundary, the direction that the simulation thinks the boundary is pointing in. And this lets us check that we actually do have the boundary lines in the right place and that they are in the right directions. And finally we have these points back here. This is a workaround to deal with the synchronization issues I had, but like I say, I've solved those, so I can probably make that go away now, so that's good. Ignore those whenever you see them, but hopefully by next week they'll be gone. So I just wanted to say, with this kind of programming, visualizing intermediate results like this, like these boundary points, the user will never see these direction lines. It's incredibly valuable because what your code is doing and what you think it's doing are very often not the same thing. And in non-graphical code, if you're, say, doing an API for a website or some sort of form to fill in or something like that, it's very easy to see what's going on. You just set breakpoints, debug things. That's very hard with this kind of programming because you have 250,000 plate points in this simulation, and if 3 of them are wrong, how on earth do you break in and debug them? And there's tricks you can use to do that, like you can kind of figure out conditions when things are wrong and set breakpoints within the conditions, but fundamentally just drawing it to the screen and seeing what exactly is being drawn and what's happening, I find to be by far the most useful way to approach this problem. So the visual equivalent of printf debugging. So yeah. So what's next? Finally, we looked at fault type determination. So is a fault convergent, divergent, or transform? So figuring out the algorithm for this was surprisingly tricky, and what I eventually landed on was, are both of the plates moving roughly parallel to the boundary? If they are, it's a transform fault. If they're not, are the centres of mass of each plate getting closer together or further apart? If they're getting closer together, it's a convergent fault. If they're getting further apart, it's a divergent fault. So let's have a quick look at this running. So here we have a video. We can see our boundary rendering mode again, and we're just going to look at some plate pairs and some boundaries and see how they're being classified. So our first pair is this pair here, and as you can see, they're pointing towards each other, and we have a convergent boundary. Blue is convergent. This represents an ocean trench, so that's working. And then we have this one here, moving apart, and that is a classic divergent boundary, represented in red. And finally 2 points, 2 plates sliding past each other parallel, and we get a white transform fault. Now, a couple of other interesting scenarios to look at here. We have 2 that are moving in the same direction, but we're still classifying them as divergent. Now if you look, this arrow is very slightly thicker than this arrow. It's hard to see, and I want to improve the rendering of this, but it is. What this means is that this plate is moving faster than this plate, and so they are spreading apart even though they're moving in the same direction. Finally, we have a convergent boundary here. What's interesting about this is one plate is indeed moving towards the other, but this plate here is parallel. Now this is correct. This is what we want to happen, because if you think about what would be happening here, this plate is either subducting underneath this one or it's overriding it, even though this plate is moving completely parallel. And we do see situations similar to this on the real Earth. So we wanted to be able to capture that behaviour, and our rules do indeed do that. So that's where we've got to. We now have the correct boundary types. So the question is, what do we want to do next? So the answer is we want to implement some behaviour that is specific to the boundary type. So we want to drive the crust formation from the boundary type. So at the minute, crust forms wherever there's a gap and wherever it will fall within the plate rather than outside the plate if it's formed and moves. And this mostly works, but it's not overly realistic. What really happens is that crust forms where plates are being pulled apart, and that was a proxy to try and do that without moving boundaries. Now that we have moving boundaries, or at least classified boundaries, we know which faults are divergent faults, so all we have to do is, for each point along a divergent fault, see if there's a gap in the crust, and if there is, add a point. Much simpler, should be much more reliable. Then we want to determine induced subduction in a similar way. So currently induced subduction happens in any plate that that passes outside, any point that passes outside of its plate. That will trigger induced subduction. We've talked about that in the past. Now, what we actually want to do is find out, is this a convergent boundary? And if so, only the points on one side of that boundary will actually form induced subduction, specifically the ones with the higher density. The plate on the other side will override, and so it will not begin to subduct. And this is really important, so we need to make that work. We need to move the boundaries to fill in the gaps. So you imagine the situation we just looked at, where one plate is moving parallel to the boundary and the other one is moving perpendicular to it. Now, the one we looked at was convergent, but if you imagine that was a divergent fault, you would have the fault start to move. It would sort of split the difference between the two plates. So both the plate that was moving parallel and the one that was moving perpendicular would have fresh crust forming along that boundary, and the join between them would move with about half the speed of the diverging plate. So we need to make the boundaries move to do that. And finally, we want to ignore transform faults. So currently, any transform faults where there are gaps will have fresh crust generated, and any where there are points moving outside of the plate will form induced subduction. That isn't what actually happens at transform faults. At transform faults, what largely happens is these are relatively small gaps or overlaps, and so you just get expansion and compression, either filling them or removing overlaps, well, preventing overlaps from forming. So we're going to just ignore transform faults, and this classification gives us the ability to do that. So how much of that I get through next week, I don't know. My time is likely to be quite limited for the next month and a half, but I'll do what I can, and still make good progress this week. I'm quite pleased with where we are. As usual, thanks for listening. Hope it was interesting, and welcome any thoughts, comments, or suggestions. Thanks everyone. I'll see you next week.